invitation. And today I'd like to talk quantum gravity and naturalness. And this work was done with Yuta Hamada and Kinya Oda and Kei Yagyu. So this is a plan of my talk. So it consists of 3 parts. In the first part, I explain the Higgs at Planck scale. And then I would like to discuss fine-tunings by nature itself. And finally, I discuss emergence of weak scale from Planck scale. And I don't think I have time to go through this subject, but in the note, these 2 parts are added. So I'd like to start from Higgs at Planck scale. So we know standard model is good to high energy scales. And experimentally, LHC told us that the standard model is good, at least below a few TeV. And we have no signal for new particles or physics, and especially we have no indication of low energy supersymmetry. And theoretically, the ultraviolet regions of the standard models can be analyzed by the renormalization group technique, and we see no contradiction below Planck or string scale. So this is a picture. So the horizontal axis is log of cutoff scale, and the vertical axis is bare coupling. So we know all the couplings are small, everything is small, and the perturbative picture is very good up to the Planck scale. Planck scale is around here. So SU3, SU2, and even top Yukawa is decreasing. And U1 is increasing, but the value is not so big. And this is a Higgs self-coupling multiplied by 8. So this is originally small, but still this is decreasing. And also this one is a Higgs bare mass. So it is natural to imagine that the standard model is directly connected to the string scale dynamics without large modification. This is what we call desert. So actually, as we will see in the next 2 slides, or the renormalization group analysis indicate a sort of triple coincidence. So actually, the 3 quantities, bare Higgs mass and a beta function for bare Higgs coupling and the beta function for it and bare Higgs mass become 0 around the string scale. And this means the Higgs potential becomes flat like this, or 0 like this, around the string scale. And actually, this was predicted by Frogat and Nielsen some years ago, based on some principle called multiple point criticality principle, which we abbreviate as MPP. So this is a picture. So this is a log of cutoff, and this is bare coupling. And this picture depends on the top Koch mass. So this value is a bit old, but now the value is 172.4 plus minus 0.7 something. But so it's not so different. And Higgs mass is around 125. So this is a coupling, self-coupling for lambda. And this is a beta function for lambda. And both of them come close to 0 around the string scale or Planck scale. Here, I say string scale for 10 to 17 GeV and Planck scale for 10 to 18 GeV, but anyway, they are not so different. And this is a bare mass square, and again, this becomes 0 around the string scale or Planck scale, but it's a bit bigger, but anyway, these 3 quantities tends to 0 around the Planck scale. And this is a picture for the Higgs potential. So the horizontal axis is renormalization scale mu, or the value of Higgs field. And the vertical axis is the value of potential. And both are in linear scale. So this is 1 multiplied by 10 to 70 GeV and 2 multiplied by 10 to the 17th and so on and so forth. And the vertical axis is 2 multiplied by 10 to 64th GeV fourth and so on and so forth. And anyway, the point is the potential looks like this. And the point is if we change the top quark mass a bit, then potential changes rather drastically. And please don't take these numbers too seriously because there are a lot of sources for errors. So, but the point is if we change top quark mass a bit, then the shape becomes different. So this is a flat, the case that potential becomes flat. And this is a case that two vacua degenerate. And if we decrease top quark mass a bit, then we have a potential like this. So as we have seen, Higgs potential may be flat around the string scale. So it suggests that the Higgs field can play the role of inflaton. So here I will introduce two attempts about Higgs inflation. One is a sort of toy model. It's called critical Higgs inflation. And Hamada, Oda, Park, and myself did it. And also independently, Bezrukov and Shaposhnikov did the same thing. So what we assume here is nature does fine tuning so that the Higgs potential becomes flat around the string scale. And secondly, we can trust the Higgs potential, including the string scale. As we have seen, the flat potential appears around string scale. So in the real physics, string dynamics switches on around here, but here as a toy model, we simply trust the Higgs potential, including the string scale. And the third assumption is we introduce a non-minimal coupling like Xi R H square, and Xi is of order 10. And Higgs is a Higgs field, and R is a scalar curvature. Then we can make a realistic model like this. So this is the potential I have shown just before. But here we introduce non-minimal coupling. So if we go to the Einstein frame, essentially what we have is we stretch horizontal axis like this because of this factor that comes from switching to Einstein frame. So the potential becomes flat around here. And the point is even for a rather small value of Z around 10, we can make a realistic inflation. And second attempt about Higgs inflation is general bounds. So this time we trust the effective potential only below the string scale and try to make bounds on the physical parameters. So here we assume Higgs field is the inflaton and the inflation occurs beyond the string scale, 10 to 17th GeV. And this time we just trust, we can trust field theory below the string scale. So we then have a lower bound on the vacuum energy at the inflation. So this is a picture. So this is the Higgs field. And here we have a string scale. So we simply trust field theory below the string scale. So this part is described by field theory, but this part we don't know. But in order to get a slow roll, and H should roll down to 0. So we have maybe inequality. We have an inequality like this. So the inflation, the value of potential at inflation should be larger than the value of potential here. So the maximum value of this part. So we have this inequality, and because the value of potential at inflation is proportional to the tensor perturbation like this. Tensor perturbation is proportional to equal 0.068 and V inflation. But this is in Planck in it. And also we know that scalar perturbation. This is 2.2 cross 10 to minus 9. So we have the ratio R is 80 over 8S, but V inflation is greater than this. So we have this inequality for R. And in terms of GV, or this one divided by this becomes this value, 3.2 cross 10 to 16 GV to the fourth. This is around the gut scale. So this inequality gives a rather strong constraint. So we can obtain bounds on possible modification of the standard model. So for example, we can consider the standard model plus simple Higgs portal scalar dark matter. And then we have this kind of picture. So the horizontal axis is dark matter mass. And this is essentially from this equation. And this means if mass is large, in order to explain the Redick abundance, the coupling, this coupling S squared to H squared must become large. So they are proportional. So the horizontal axis essentially means the value of kappa. Now, at any rate, if we fix a model, we can calculate the Higgs potential, and from that inequality, we have this kind of curve. Here, these curves correspond to the fixed value of top-cope mass. So if top-cope mass is around 170 around here, so we have this curve. And the vertical line is from potential positivity. So if the value is around here for top-cope mass 172, so the potential is unstable. So the value should be on the right hand of this. And this curve is a maximum value of the potential. So the inflation scale must be upper side of this. So this part is allowed. So if we change the top-cope mass, and we have this excluded part, and this part is allowed. So something like this. And we do not insist on this kind of model, but what I want to show here is once you give some model, and from that inequality, we have rather strong constraint. So this is a short summary for the standard model around Planck scale. So first, the standard model is valid to the string scale, at least theoretically, and the standard model might be directly connected to string theory without large modification. And also, as we have seen, Higgs field is near the stability bound. So potential is almost flat. And also the bare Higgs mass is close to zero at the string scale. It implies that Higgs is a massless state of string theory. And Higgs cell couplings and its beta function become zero at the string scale. And this means Higgs potential can be flat around the string scale, which suggests the Higgs inflation. So then I'd like to discuss the fine tunings by nature itself. So there are several attempts to extend the conventional framework of the local field theory in order to solve the fine tuning problem. So there are several attempts, and maybe there are more. So one is asymptotic safety, and this is a multiple point criticality principle, which I would like to explain here, and classical conformality, and baby universe, and multi-local action. So, and they are more or less related. And today I would like to start here, multiple point criticality principle, and discuss the relation to classical conformality. So what is MPP of Frogat and Nielsen? So this is the statement of MPP. So imagine a system that is described by the path integral of not the canonical ensemble, but the microcanonical ensemble, or an even more general ensemble, like this. Now, this one I will explain the next slide. So this is the original path integral. For Euclidean time, usually we start from this path integral. But in statistical mechanics, we know this canonical ensemble is equivalent to micro-canonical ensemble. So this is the idea. So, and also even more general path integral like this. Here, f is a function of S1 phi, S2 phi, and so on and so forth. And each SI phi is the action of local field. I will come back to this in the next slide. But anyway, so we consider this kind of path integral.
Excuse me, Kawai-san?
Here is still the system is equivalent to the ordinary field theory in the large space-time volume limit. So this is something like statistical mechanics, the equivalence between them.
Excuse me.
In some sense, this is not so surprising. So the point is, but the parameters of the corresponding field theory, so this field theory, are automatically fixed, such that the vacuum is at a multiple criticality point. So this is a statement of MPP, and I would like to explain why it happens in the next few slides.
Excuse me.
Yes.
When you go from the canonical ensemble to micro-canonical ensemble, what happens to the this kind of weak rotation? I mean,
okay, yeah, that's a very good point. So I think later I will discuss in the Lorentzian space, and I will discuss equivalency in the Lorentzian signature. So here the signature, Euclidean or Lorentzian, is not so important here. So I will come back to Lorentzian signature later. Thank you very much. It's a very good point. So in fact, we can show that the low energy effective theory of quantum gravity or string theory is given by the multi-local action. So this was done by Coleman long time ago, and also from matrix model side, we can reproduce this low energy effective Lagrangian. So there are several reasons to believe this low energy Lagrangian, or maybe I should say the low energy effective action. So effective action is a function of S1, S2, and so forth. So if we expand this, so this is linear in local action, and this is quadratic and cubic, and so on and so forth. And each SI is a form of action of a local field theory. So we have a integration over space-time and square root of metric, and some local scalar operators, such as if we take one, this is nothing but the cosmological constant term. And if we take R, so this is nothing but Einstein-Hilbert action. And if we take F mu nu square, this is nothing but action for gauge field, and so on and so forth. So the point is, effective action is a function of local action. So this is the point. So this is first obtained by Coleman by considering wormhole. So if we consider the effect of wormhole, we have a sort of a bilinear, bilocal field. But this bilocal means integration over x multiplied by integration over x. So this bilinear means just bilinear of local action. So essentially there is no non-locality. So we have just local action and some function. So this is the point. So in the appendix of this note, I show the derivation of this, but maybe today I don't have much time to explain about this. So I would like to start from here. So because S effective is a function of SIs, we can express the exponential IS effective by a Fourier transform as this. So here, lambda i's are Fourier conjugate variable to SIs, and W is a function of lambda i's. So please note here that lambda i's are just numbers because Si is an action. So this is just a number. So lambda i's are number. So lambda i's are not field, but a number. So this integration is just over d lambda 1, d lambda 2, and so on and so forth. And this is just a function of lambda 1, lambda 2, and so on. So then the path integral for S effective, this one becomes like this. I just interchange the order of lambda integration and phi integration. So we have a lambda integration with a weight W, and we have a path integral for phi for this action. So the point is because all i's are local operators. So SI is just the integration of those local operators. So this combination, summation I lambda I SI, is an ordinary local action. Okay, because SI is just something like this. So if we sum lambda I SI, we have just one spacetime integral and the summation of the linear combination of these ones. So essentially, this is just an ordinary local action. But here, lambda I are regarded as a coupling constant, okay? Because we multiply lambda 1, lambda 2, lambda 3, and so on, so forth. So lambda I is essentially the coupling constant of this local action. So therefore, the system is the ordinary field theory, but we have to integrate over the coupling constant with some weight W.
Excuse me, Kawai-san.
Yes.
Is this weight function W lambda is non-negative definite, semi-positive definite?
Yeah. Okay. So that point. Okay. I do not know exactly, but if we see the next argument, what I want to show is this form of W is not so important. So I will come back to this problem. Okay. So the point is, if so this integral is okay. So if various lambdas remain in this integral, then this is no longer a field theory, local field theory. But the point is, okay. So the point is, okay. So I'll come. Okay, I'll come back that problem. But the point is, okay. Here, this is our integral, and we have seen that this path integral can be written like this. Okay, this part is ordinary field theory with coupling constant lambdas. And we have some weight function W, and we integrate over lambda. So this is a general form. So the point is, if a small region around lambda 0 dominates this integral, then it means that the coupling constants are fixed to lambda 0. So in that case, the global behavior of W lambda is not so important. So we just need the value lambda 0. So W is not very important if this happens. But of course we do not know whether this happens. So we have to be careful. But so for the positivity of this, at this stage I do not know the answer. So, and actually, in order to investigate this path integral carefully, I think eventually we need such information. But here, I would like to pursue the possibility that a small region dominates in this lambda integral. So actually, that is a very important point. Okay, so we can give some explanation to MPP from this argument. And the essence is we can approximate G lambda like this, exponential minus IV, V is the spacetime volume, and E vacuum lambda. This is vacuum energy per unit volume. And this is because our universe has been cooled down for a long time. So our universe is very close to the ground state, and for a long time, we have ground, some state close to the ground state. So we can approximate the partition function like this. So V is large, and the vacuum is vacuum energy per unit volume. So if this function E vacuum lambda is smooth and has an extremum at lambda c like this. Okay, this is horizontal axis lambda, and vertical axis is vacuum energy per unit volume. So if this function looks like this, the stationary point dominates, and we have this expression. So we have highly oscillating. So here I'm considering Minkowski signature. So I should have mentioned. Right? So I'm considering Minkowski signature. Okay. So the argument is essentially the same for Euclidean, but here I consider Minkowski signature. So we have this highly oscillating function, and we have lambda behaves like this. So this is quite standard argument that if V is very large, so this function is replaced by delta function at the minimum, and the error is about 1 over V. So in this case, lambda is fixed to lambda c in the large volume limit. So this is a very simple case that this indeed happens. Once we have this form, then lambda is fixed to lambda c. So this is a very simple principle that lambdas are fixed in such a way that vacuum energy becomes minimum. And second possibility is kink. So in this case, the function of E vacuum of lambda behaves like this. So we assume if E vacuum lambda has a kink, and we assume in the both sides, the function is monotonic. So, but need not be an extremum. And this can be extremum, but need not be. So we just have kink. And then in this case, again, if V is very large, we can approximate this function by this kind of form. Here we have delta lambda minus lambda c. Again, the integration dominate around lambda around lambda c dominate in the integration. And the value is 1 over exponential vacuum energy vacuum prime lambda c minus lambda c minus 0. So this picks up a jump of the 1 over first derivative in the both hand side. And this can be easily seen from this integral. So if we consider this integral from a to b dx exponential ivx phi x, phi is a test function. So by applying partial integration, so first we integrate this, so iv 1 over iv exponential ivx and phi x, and we consider the value of b and a. And then we have this one multiplied by phi prime. And then by repeating this, we have 1 over v expansion. So we have this expression. And if it's monotonic, we can replace x with fx. And so if we replace this x with fx, then this integral is dfx divided by 1 over f prime x. So by putting 1 over f prime x, we can use this formula. So and the error is 1 over v squared. So we use this formula for this part and for this part and sum up. Then we have all this expression. So this part comes from the formula used for this part. So we have the value at lambda c plus 0. And here we use this formula for this part. So we have this value. And the relative sign is minor. So this is something like this. So in this way, also the lambda is fixed to lambda c in the large V limit. And this is essentially the original MPP, because in this case, the energy is so this is a first order phase transition. So this is essentially the original MPP. So we consider very simple cases, but if we consider the time evolution of universe, the definition of Z lambda is not a priori clear. So for example, we need to specify the initial and final states. However, even if we do not know the precise form of Z lambda, we expect that Z lambda is determined by the late stage of the universe, because most of the space-time volume comes from the late stage. So from this, we can make some predictions on lambdas under some circumstances. So here we consider two cases. So one is some symmetry, and the typical example is QCD theta parameter. And actually, this argument was done around 1990 when people were talking about baby universe of Coleman. So this argument is essentially the same as Nielsen and Ninomiya at that time. So the point is, so this parameter, theta QCD, becomes important only after the QCD phase transition. But then the masses and lifetimes of hadrons are invariant under the change of theta QCD to minus theta QCD. So we expect that the partition function Z is even in theta QCD. So if theta QCD behaves like this, not like this, so we don't know which one is realized, but if theta QCD behaves like this, then theta QC is tuned to 0. So in this sense, anyway, in probability 1/2, we get theta QCD 0. So this is the argument of these people. And the second possibility is edge of drastic change. So this time we consider the following situation. So physics changes drastically at some value of the coupling. So this is coupling, and this is Z. And actually, so as I said several times, so we don't know the exact form of Z, but suppose we know physics changes drastically at some value. Then we have something like this, and suppose Z is monotonic elsewhere, then the coupling are tuned to the value lambda C, as we have seen for the kink just before. So the examples are, there are several examples of this situation. One is a cosmological constant. So if a cosmological constant is negative, we have this kind of closed universe. But if cosmological constant is positive, we have open universe. So we have a drastic change between these two. So probably we have a situation like this. So the cosmological constant is fixed to the boundary value of this, that is lambda equals 0. So this is an explanation for the cosmological constant based on this principle. And also we can consider Higgs inflation. As we have seen, if we tune the parameter, for example, if we tune topic of mass, we have this potential or this potential or flat potential. And but if we consider inflation caused by this potential, and if potential is like this, the inflation stops in very short time, and if potential looks like this, inflation stops here. So the flat potential is the boundary value of Z. So again, the parameters should be chosen in such a way that potential becomes flat and inflation occurs. So this is one explanation why we can consider the Higgs inflation, as we have discussed. So also classical conformality can be explained in this context, and I will come back to this problem. So in this way, we may introduce the generalized MPP. So the statement is coupling constants, which are relevant in low energy region, are tuned to values that significantly change the history of the universe when they are changed. So this is a generalized MPP we use here. So, but still there are many open questions. And for example, for Higgs field, we have seen if we tune parameter, we have a potential like this. This is the original Frogat and Nielsen. So in this case, we have first order phase transition. And also if we consider inflation, again, this is a sort of critical point. But we do not know which one is favored by nature. And also, even if we explain the fine tuning here, we do not have any mechanism to explain the origin of the weak scale, why we have 100 GeV here. So I will come back to this problem. And so also with small cosmological constant, and in this argument, if we believe this literally, cosmological constant is fixed to 0. But we know we have some small cosmological constant. So there should be some modification to that argument. And also, we don't know how many parameters are tuned. And if all the parameters can be tuned, probably the minimum value of energy is obtained by free field. So everything becomes free. So this is actually the reason why they lost interest in Coleman's baby universe. So if we have too much big fix, so everything might become trivial, just free field. So we have to be careful about it. But at any rate, to answer these questions, we need the precise form of Z lambda. So this means we should investigate the wave function of multipath. So I think the question about the positivity of W becomes important if we try to understand Z lambda completely. So finally, I would like to discuss emergence of weak scale from Planck scale. And, so basic assumptions we introduce here is the standard model is directly connected to the string theory without large modification. So we have some standard model with small modification, which I mean by plus. And at string scale, this one is changed to string dynamics. But the assumption is the low energy field theory standard model plus is valid up to string scale. And the fundamental scale is only the Planck or string scale, which appears as a cutoff of the field theory. So at here, the theory is switched to string theory, but from this side, the MS looks a kind of cutoff. So we introduce, so this part is described by local field theory with some cutoff at the string scale. And also, this is MPP, so generalized MPP, so relevant operators. So I borrow the terminology from denomination group. So the relevant operators means couplings with positive mass dimension. So relevant operators are tuned by nature itself through the generalized MPP. So the question is, how does the weak scale appear in this context? So this is, I think, everybody's guess. Weak scale should appear as a non-perturbative effect. Then it is related to the Planck scale like this. This is Planck scale and non-perturbative minus constant over G coupling. So if GS is small, this can be large. So you have minus. So this is very small. So we can explain large hierarchy in some sense in natural way. So the problem is find a phenomenologically acceptable mechanism to show this. So actually there are various possibilities, and the first one is a QCD-like dimensional transmutation. And actually in QCD, we have this formula. The QCD lambda parameter is obtained like this. Lambda is cut off and exponential minus constant divided by G0 square. And actually, so QCD lambda parameter could be around 100 MeV, and lambda could be very large, like Planck mass. But this one is not compatible with weakly coupled Higgs. We know experimentally, and Higgs is weakly coupled. But this is something like a QCD. So low energy effective theory becomes a strongly coupled theory. So it is not very easy to get a weakly coupled Higgs from this mechanism. So actually this is something like technical around those things, but now we know Higgs are weakly coupled. And of course, still there are some possibilities to pursue this possibility, but here I will consider a different possibility. So the second one is Coleman-Weinbach mechanism. So original idea is to explain spontaneous symmetry breaking of the standard model from the massless Higgs. But this is not acceptable because in this case, in the ordinary Coleman-Weinbach, so Higgs mass becomes much smaller than the Higgs expectation value. Actually, this is one loop comes from one loop effect. So this is usually very small compared with this. And I will come back to this problem. But anyway, so the one way to avoid this problem is to consider additional gauge field plus additional complex scale. So, and we make a mass scale by Coleman-Weinbach mechanism independently to the standard model sector. Then we transfer the mass scale to the standard model through the coupling to the wave of this field. And this is actually possible, and we can make a lot of acceptable models. But if we take this approach, there is an even simpler model. So instead of considering additional gauge and additional complex scalar, two real scalars suffice. And actually, this model was discussed several people in several different contexts. But anyway, we consider two real scalars. So this is some additional field, something like additional gauge field plus complex scalar in Coleman-Weinbach. So we consider two real scalar, and we discuss spontaneous mass scale generation from this model, and then we couple this to the standard model. So before coupling the standard model, we have these two scalars, which I call phi and s. So the potential is something like phi to the fourth, phi square square, and s fourth. And we call the coupling rho for phi fourth, and rho prime for s fourth, and kappa for the mutual coupling. And for a while, we assume the Z2 cross Z2 invariance. Phi goes to minus phi and s to minus s. But later, I will remove this constraint for this. But anyway, for a while, for simplicity, I consider this case. But the more important assumption here is the classical conformality. So here we do not have any mass parameter, m square, phi square, m square, square, and so on. So we don't have such. So what is a classical conformality? So I would like to discuss the origin of the classical conformality. So classical conformality, so there are many ways to express a classical conformality, but here I would like to express classical conformality as this statement. The renormalized masses are zero. This is classical conformality I use in my talk today. So this sounds, in some sense, this sounds nonsense for normal field theories because there is no quantum mechanical symmetry that guarantees masslessness of scalar except supersymmetry. So on the other hand, once we accept the existence of self-tuning mechanism, classical conformality is one of the natural choices This is what I want to explain. So more concretely, we can take the MPP, coupling constants are fixed to critical points. But there are some variations in the meaning of critical points. So one is critical points for cosmological evolution. So in this case, critical values, we consider critical values that the time evolution of the universe changes drastically when they are changing. So more concretely, for the model we are considering, suppose that the universe starts from phi equal to 0. Then if m square is positive, phi equal 0 is metastable or stable. So universe remains in that state for a while. On the other hand, if m square is negative, phi equal 0 is unstable. So universe transitions quickly to another state. So the time evolution of the universe changes drastically at the point m square equals 0. So the coupling m square is fixed to 0. So this is nothing but the classical conformality. So another critical point is critical point for the vacuum energy. So in this case, we consider critical values that the phase of the vacuum changes when they are changing. So we will see that this actually happens when m squared is some critical value. So this is essentially the first of the phase transition. And I will come back to this later. So at any rate, as we will see, there are various types of critical points. So in any case, renormalized masses are fixed to some values, and we have similar predictions. And for a while, we concentrate on the case 1 of classical conformality. And later, I'll consider this case. So I would like to consider spontaneous symmetry breaking of the two-scalar model with classical conformality. So the real scalar model, we have this Lagrangian, phi square, s square, and potential is phi 4, s4, and mutual coupling, rho, kappa, and rho prime. And the condition of classical conformality is both phi and s are massless. Massless means the effective potential at the origin. The second derivative of the effective potential is 0. So this comes from this argument, right? So if we consider the evolution of the universe, so these are critical values. So I impose this. So the basic feature of this model is for a large region of the parameter space. Parameter space means the parameter of rho, kappa, and rho prime. So one of the fields, phi or s, has a non-zero vacuum expectation value, and which is created non-perturbatively from the cutoff. So this is a point. So let's see the renormalization group analysis. So in order to not to forget the parameters, I just rewrite the expression for V. Rho is parameter for phi 4, kappa is parameter for phi square s square, and rho prime is s to the fourth. And the beta function for rho is this one comes from two vertices of this, and from phi loop we have this. And this one comes from two vertices of this and make S loop. And again, we have phi 4. So we have this. And beta rho prime is rho prime square comes from two vertices of this, and from S loop, we have S4. And also from two of this, if we consider phi loop, we have S4. So we have this. So these two are the same, or we converted just by replacing rho and just interchanging rho and rho prime. And for kappa, we have three terms. And this one comes from rho and kappa. So by making phi loop, we have phi square s square. And this comes from rho prime and kappa. And again, by making S loop, we have phi square s square. And also from two vertices, two of these vertices, if we contract phi and s, we have again phi square and s square. So we have this expression. So this is a beta function. And the assumption is we have a cutoff at Planck scale. And at the Planck scale, at the cutoff, we simply assume these three parameters, so bare parameters are positive. So this is just an assumption. So we consider this scale, we have some cutoff scale, and we have this modification, and the input or assumption is at this stage, 3 of those couplings, bare couplings are positive. So then we decrease the renormalization point from the cutoff, one of the coupling constant becomes 0. So this is a picture. So this is renormalization scale and couplings, kappa, rho prime, and rho. And so they become, all of them decrease if we decrease renormalization point. So we assume rho becomes 0 first at some value, mu equal mu star. So anyway, they are decreasing. So one of these 3 becomes 0 first. So here we assume rho becomes 0 first. So actually this is possible if rho 0 prime is larger than rho 0, and then rho 0 becomes to 0 first, and then kappa 0 is much bigger than them. So kappa 0 is still non-zero around here. So anyway, so in some parameters, in some regional parameter space, so this is realized. Rho becomes 0 first. Then it is expected. Okay, so potential is this, but rho becomes 0. So if we consider one loop effective potential, I will do it in the next slide. Then phi get some non-zero expectation value. And then because of this, S becomes positive mass. S has positive mass because kappa is still positive. So the expectation value of S is 0. So in this sense, phi becomes non-zero, but S stays 0. So Z2 cross Z2 symmetry is broken spontaneously. So in order to see this, we consider one loop effective potential. Oh, sorry, the time is running. So effective potential for S equal to 0 because S is 0 eventually. So we just set S equal 0. So we have one loop potential for phi. So this is original phi 4, and this comes from rho square, and this comes from kappa square. Okay. But at the mu equal mu star, these two are 0. So we just have this potential. So this is a point. If we take a renormalization scale properly in such a way that rho mu equals 0, we have just effective potential coming from this. So this is proportional to kappa square. So the potential is just phi 4 log phi square. So potential like this. So and mu star is appears something like this: phi square over mu square multiplied by kappa mu square. So this point is okay. This point phi, this combination is 1. So phi is mu star divided by square root kappa. So anyway, around this value. So roughly speaking, around mu square, this becomes 0. So the minimum is a bit smaller than this, but anyway, some constant multiplied by this number. So in this way, a mass scale V emerges. So and the relation also, and in order to estimate the value of V, we can simply apply approximate renormalization group equation. And then we can see that V is proportional to MP multiplied by some non-perturbative form, rho 0 over kappa 0 square. So this part is not very important, so I will skip this. And also the masses of the particles, mass of phi comes from second derivative of phi around here. But the point is potential is already proportional to kappa square divided by some big number. So the mass of phi is rather small. The mass of S comes from this coupling, the B multiplied by kappa. So we have this one. So if kappa is less than 1, then the general pattern is V is larger than MS, and ms is larger than m phi because we have kappa here and kappa square here. So for example, if kappa is 0.1, the ratio between v, m, sorry, this is ms, sorry, this is ms, and m phi is 1, 0.2 and 0.006, something like this. So this is why I said the ordinary Coleman-Weinbach works for the original attempt, in the original attempt. So the mass of phi becomes much smaller than wave. So, but in our standard model, V and mass of Higgs are almost same, 250 and 125 or something like that. So, but if we do Coleman-like Weinbach mechanism for this one, we have small number. So we couple to this model to the standard model. So the total action is a standard model plus this phi s system, and the coupling is through phi h got mass. So this is, I have minus here. So if h phi has wave, so mass for m square is negative. And here we have s square and h square. And this one, the wave base is 0. So this one is not so important for the standard model. So in this way, we can have a mass from the two scalar model, and through this coupling, weak scale, so Higgs mass is generated. So this is a mechanism. So in this case, S has no wave, and S is heavy but not too heavy, like this. And also this couples to Higgs like this. So it is natural to regard S as a Higgs total scalar dark matter. So we have considered classical conformality, but we can consider the first order phase transition case. So in this case, we add bare mass or some mass parameter to the potential. Maybe I shouldn't say bare mass. Some parameter, mass parameter like this. And then in the classical conformality, we assume m squared equals 0, but so this is a case of classical conformality. But we can add mass square, and then this potential is a bit lifted. So if mc squared is small, m squared is small, we have something like this. Okay, and then if we increase m squared to some critical value, the potential looks like this, Then we have these two buckets degenerate. And now VC and M phi are modified, but just some numerical numbers. So first order phase transition point is as plausible as classical conformality. And at this stage, we cannot tell which one is favored by nature unless we know the precise mechanism of MPP. But at any rate, the generalized mass scale change only by some numerical factors. So again, we can say that the weak scale emerges from the Planck scale. So there are further generalizations. So far we have assumed Z2 symmetry for phi and S. But here I just assume Z2 symmetry for S because I would like to regard S as dark matter. So Z2 symmetry for S is kept. But we discard the Z2 symmetry for phi. So we have these parameters for, this is phi square, phi cube, because we do not have Z2 symmetry. So we can have G phi and some phi cube. And also for S square and phi S square. And we have original of phi square and S4. And also by shifting G, we can set this is 0. So essentially we have 4 parameters. So the general problem is to find some tetracritical point in the space of 4 parameters, m square, h sigma, and m prime square. So, but this is a general problem. But instead of solving this problem, we consider 2 special solutions. The first, we take m square and m prime square 0. This is because of the same argument as classical conformality. And so we set m square and m prime square 0 with some criticality condition. And then again, this sigma can be set to 0 by some criticality condition. Because if we flip the sign of sigma, the shape of potential drastically changes. So we can assume, we can consider such critical point that sigma is 0. So we have just phi q plus something. So I just consider this special critical point. So this is, if h is 0, we have this potential. And if we switch on phi cube, and this potential is tilted a bit, and then we have these two additional critical points. So this one is, okay, I magnify this part. So this one, we have some degeneracy between this vacuum and this one. And in this case, H is a bit bigger than this. So a bit lifted, then we get this shape. We have some saddle point here. But if we see the global picture, they are almost same. And actually, and in the phenomenological analysis, so these two are almost same, but slightly different. So finally, I want to sketch the analysis for the phenomenological validity. So this is a form we are considering, and actually what we want to do is to investigate all possible critical points, but instead of doing this, we consider just 4 critical points. So one is a classical conformality, and the second one is first order phase transition. So this is the one we considered. This one, I call it critical point 1, 1. This is critical point 1, 2. And also we have considered Z2 non-invariant case, critical point 2, 1 and critical point 2, 2. So I consider these 4 cases. And so, and we also take the mixing of Higgs and phi into account. And we impose the following conditions and examine the allowed region in the parameter space. So Higgs mass and wave are correctly reproduced. And this is almost trivial. And the Rayleigh abundance of dark matter is the right value, around 0.12. And perturbativity, absence of random pole up to the string scale. And also we impose a dark matter direct search bound from xenon 1T, and also LHC bound for scalar particles. So and in this analysis, we use this program, but I'm not an expert. So this part, I cannot say anything precisely. But anyway, the result is very simple. And actually, so we have 5 extra parameters. This one, compared with standard model. So we have 1, 2, 3, 5, 4, 5 square, 5 S4, and coupling to the Higgs. So we have 1, 2, 3, 4, 5 extra dimensionless parameters. And also we have 4 dimension full parameters. But as we have seen, dimensional parameters are fixed by MPP. So they are fixed to various values corresponding to the cases. So we consider. But the point rho is replaced by phi by choosing a renormalization point to the point where rho vanishes. So rho is replaced to V phi. And rho prime has a small effect in low energy. So they just describe scattering between dark matter. And Higgs mass is obtained after diagonalizing the mass between, diagonalizing the mixing between phi and H. So this gives one constraint. And also dark matter mass is obviously seen from here. This comes from Higgs wave and phi wave. So the linear combination of Higgs wave and phi wave. Well, so this is just converting parameters to ms square. And also the Lyric abundance gives something like this constraint. And this means the annihilation cross-section of S is proportional to the mass of M. So this one is kappa square is annihilation cross-section, so SS to phi phi. And this one is SS to HH. So annihilation cross-section should be proportional to MS square. So we can check this by numerical calculation. Anyway, the result looks like this. So we have 5 parameters and 3 constraints, 1, 2, 3. So we have 2 parameters left. So this is a picture. And, so the horizontal axis is the mass of S. So this is dark matter mass. And the vertical axis is mass of phi. So after resolving the mixing between phi and H, so Higgs mass is already fixed, 125. So this is the mass of the other scalar field. So this is a case of critical point 1, critical point 1, 2, and the critical point 2, 2, and 2, 1 are almost same, as we have seen from the picture of the potential. So this is the allowed region. So the point is from Lyric abundance, the red region is excluded. And this gray region is excluded by perturbativity. So red region and gray region are excluded. And then we have this region remain. But then this is bound from xenon 1T. So this is a direct search. This part is removed. And this part is removed by LHC. So the reason is if the other scalar is close to the mass of Higgs, then they mix largely, so they can be detected. So this region is excluded. So green region is excluded. So we have the white region left. So in this sense, the model is still valid. And and the good point is we have 2 parameters left. So we do not know MS and MH, large MH is the other singlet scale. So we have this plot. And this line is value of wave of phi. So if so anyway, we have 2 parameters left. So if parameter is something like this here, this means wave is black one is wave is 10 TeV. So something like this. So at any rate, this model is still valid. But the point is this dotted curve is if we make the stronger perturbativity condition. So this means all couplings are less than 10 for the mu less than 10 to 18. So this gray zone, the condition is we have no random pole up to 10 to 17. But if we make this stronger condition, then the gray zone becomes this dotted line. So this means this is almost excluded. So this part is quite subtle. So perturbativity. So at any rate, we have some strong constraint on perturbativity. So this is the situation of this model. So I would like to finish. And so in wide classes of quantum gravity or string theory, the low energy effective action has a multi-local form, something like this. And the fine-tuning problem might be solved by the dynamics of such action. But we need a good definition of the path integral for such action. But as an ad hoc assumption, we can consider the generalized MPP and make non-trivial predictions. And by considering minimum modification of standard model based on MPP, we might reach the right low energy theory. So I'm sorry, I have used too much time, but anyway, I would like to stop here. Thank you very much.
Thank you very much, Professor Kawai-san. So if you have a question, then please turn on your mic and camera and ask. So please, any questions?
I have a question.
Yes.
So about the inflation sector. So if you, well, I think you're implicitly assuming the inflation happens in the Higgs sector.
Yes.
So, and assuming the non-minimal coupling to the gravity.
Yes.
But non-minimal coupling battery breaks the conformal symmetry. So, so is that, are you implicitly assuming it's a sort of exception in terms of the conformal symmetry argument?
Oh, okay. So the point is, okay. So to add non-minimal coupling breaks conformality. So is this the point? Oh, yes. Yeah. Okay. So I have no good answer to that, and actually, as we have seen here, yeah. So this is sort of toy model, I should say, because we can trust local field theory just below the cutoff scale, so string scale, right? So we cannot use the local field theory exactly beyond the string scale. So at least if we go beyond the string scales, string dynamics comes in, and their string scale has a explicit meaning. So in this sense, above the cutoff scale, I think, honestly speaking, we shouldn't trust local field theory. So maybe this is just a model to incorporate string dynamics. So instead of solving string dynamics properly, we just approximate the string scale dynamics by this non-minimal coupling. So actually, I myself think we shouldn't trust this argument so much. But instead, this argument is just based on inequality. So this argument can be trusted. And still we have some strong constraint on this. So honestly speaking.
I see, yeah. I see. Yeah, thank you. And also I have another question. It's not actually a question, but do you have any comment on a cosmological constant based on this argument?
Okay, so that's also a very good question. And we can try some argument to explain a small cosmological constant based on some sort of MPP. And one possibility is to consider, sorry, which one? Yeah. So one possibility is the following. Okay, so if we consider just four-dimensional space, then cosmological constant 0 is some sort of critical value. But if we consider some sort of fifth dimension, and maybe we can explain the smallness of the cosmological constant. And actually, we wrote a paper about this, but I don't think it's so successful. But so again, honestly speaking, anyway, we need a precise form of Z. So this is the right attitude. But somehow this argument is not so bad. Cosmological constant is very small. So we have to give some good analysis for Z. So this is all that I can say. So.
I see. Yep. Thank you.
Thank you.
So, quick question. So, Professor Kawai, this is John. So I'm not sure if my question makes sense, but let me have one. So for the classical conformality, for example, the entropy says that m squared is 0. But does this principle also predict m squared is 0 at which scale, or does it just
okay. So yeah, that's a very good point. So the classical conformality, there are many ways to state classical conformality, but okay, so this one is okay. Yeah. Okay. So here, okay, the assumption we take is the following. So the classical conformality means m squared at phi equals 0 is 0. If we start from this argument, so critical values, that the time evolution of the universe changes drastically. So if we take this definition of critical point, then in the effective potential at phi equals 0, so this m squared means second derivative of effective potential at phi equals 0, right? So in this sense, so the classical conformality in this context is the second derivative of the effective potential is 0. So I think there are many people are thinking about classical conformality, and some people say the mass square at Planck scale, at cutoff scale is 0, and then they give some argument. But the argument we consider here is just this. I think if we take this kind of argument of generalized MPP and MPP, I think this definition of classical conformality is more natural. But anyway, it depends on what theory you think you consider. So for us, we take this assumption for classical conformality.
So the initial condition of the universe evolution is more related to this principle.
Oh yes. So this is yes. So this is a generalized MPP that we propose. So the reason is we are considering some sort of partition function, but we do not know the form explicitly, and because we have to do this kind of path integral. So we do not know the exact form, but maybe so this is just a hypothesis, and so the coupling constant, which are relevant in low energy region, are tuned to values that significantly change the history of the universe when they are changing. Then the reason is if the coupling changes, then the history changes. If history changes drastically, then Z should change dramatically. So this is the reason why we consider this generalized MPP. But it depends on what kind of history you consider, right? So in this case, we just simply assume if universe starts from phi equals 0. But if we consider different universe, phi equals 0 is not so important. So this is not so important. So again, this point is not very crucial, not very clear. But at least here, if we assume this, and we can say m squared 0 is critical. So many things depend on the situation you consider. So I think this is just one possibility. So actually we don't know which one the nature takes which one, the classical conformality or first order phase transition. So actually, so in order to see which one is taken by nature, we know explicit evaluation of Z lambda. So, but at any rate, at least we can say these two are critical points in some sense. So the project, what I wanted to say is, at any rate, if we consider two-scalar model, we have these parameters. So in these parameters, or in principle, we can classify all possible critical points and then compare what kind of, compare the physics they describe. So in this sense, I said, so by considering a minimum modification of standard model based on MPP, we might reach the right low energy theory. So anyway, this is just an attempt. But once you fix a form of theory, the number of parameters are fixed. Then we can, at least mathematically, we can classify all possible critical points. And here we consider just 4 critical points, but in principle, we can consider all possible critical points. And then we can do some phenomenological analysis. So anyway, what I can say now is very weak, but I hope this shows some direction to go, and at least this problem is this problem itself can be solved. So maybe it helps to make the right low energy theory.
Sure. Thank you very much.
Thank you.
So I have a question.
So
your argument is based on MPP, and can you, for example, apply this argument to some couplings or some numbers we already know, like top quark mass or? And another question is,
oh yes,
it seems there is a little, some small similarity with the Anthropic Principle.
Oh yeah, yes. Yeah. So it's also a very good point, and yeah. So based on the question is, so for example, if we can explain the ratio between lambda parameter and Higgs wave, something like this, right?
Yes.
Yeah. So I think it's a very good point, and there are some attempts to explain physical quantities, observed quantities, but as far as I know, there is no very good success. And actually, we have tried to explain the ratio between lambda parameter of QP and scale based on maximum entropy principle. And maximum entropy principle is close to maximum multiple point criticality principle, MPP. And maximum entropy principle is a bit different, but still we consider the function z lambda. Sorry, z lambda. This is z lambda. But the point is, so if we consider the quantum universe, we have some multiverse. So in each universe, we have this z lambda. So we have many universes, and each of which has some special value lambdas. So the question is, in order to make z lambda maximum, then this means, in some sense, this means we make the entropy of the universe maximum. And so the point is, we have many universes, and if we choose one universe randomly from it, so if that universe has big entropy, the possibility to pick up that universe is large. So the argument is something like this. So in addition to this, we can put maximum entropy principle that the entropy of the universe at a late stage should become the maximum. And then we can say something about the parameters. So based on this, for example, if we assume the standard cosmology, then at the late stage of universe, proton decays and so on and so forth, and then we can estimate the entropy of the late stage of the universe. And then we can see what kind of parameter gives the largest maximum and largest entropy to the late stage of the universe. Something like this. So again, this is very ambiguous, but still we can say something. But I think we haven't reached the stage that everybody agrees. So anyway, we're just struggling.
Okay.
Yeah.
Yeah, thank you very much for very interesting talks.
Yeah, thank you very much.
Any other question? I think then okay. Let's speak up again. Thank you very much for nice talk, Professor Kawai-san.
Yeah, thank you very much for listening.
Thank you very much.
Yeah.
Bye bye.
Thank you.
Yeah, bye bye.
Bye bye.